In this video, we're going to begin exploring the chemistry of hydrogen-containing compounds, and we're going to focus on 4 general reaction types that differ in the types of bonds made and broken, how bonds are made and broken, and then whether oxidation and reduction occurs, whether electron transfer is taking place. So the first 3 categories have to do with how bonds within the hydrogen-containing compound are actually broken. There's heterolytic cleavage by hydride transfer or proton transfer. We'll talk about what these mean here in a second. There's homolytic cleavage, which is fundamentally different from heterolytic cleavage in a way that makes sense if you think a little bit about the Greek prefixes involved. And then there are oxidation and reduction or redox reactions. And we've talked a lot about these already, but in the context of organic chemistry in particular, the formation and cleavage of bonds to hydrogen versus oxygen or other more electronegative elements is a place where oxidation and reduction shows up a lot. So we're going to touch on some general principles of oxidations and reductions of organic compounds that will hopefully be useful for you in your ensuing organic course. But let's start with heterolytic cleavage in general. So the idea of heterolytic cleavage, sort of fundamentally, is that a hydrogen R bond, where R is just absolutely any atom, can split unevenly. The 2 electrons in the hydrogen R bond can go to R or can go to H. And so in this uneven split, we can have a situation where H does not retain the electrons, R retains the electrons, and H plus breaks off and it's transferred somewhere else. This is called proton transfer. And notice here the curved arrow is showing that the electrons in the HR bond are going towards R. This is how we end up with a new lone pair on R and a negative charge there. And H plus is left behind, and generally something would come in and bond to that H plus at the same time. It's also possible to break the HR bond sort of in the opposite direction, giving both electrons to H to create H minus, or the hydride anion, and R plus. And this is still heterolytic cleavage since the bond is breaking unevenly, but now both electrons are going to H rather than R. And hydride, the hydride anion, is either generated or transferred somewhere, and so we think of this as hydride transfer. And so these are the 2 fundamental types of heterolytic cleavage that we see in the context of hydrogen-containing compounds, either proton transfer or hydride transfer. And already from the charges involved on the product side and how electrons are moving, we can get a sense of the types of hydrogen-containing compounds that engage in these reactions, right? This looks like Bronsted acidity, and this looks like generation of the hydride anion, and this is evocative of our covalent hydrides, and this looks like an ionic hydride type situation, and we're going to be making those connections through the remainder of this video. Heterolytic cleavage by hydride transfer specifically refers to the situation where hydrogen retains the electrons. And so this is a reaction type that's typical of compounds in which hydrogen is already significantly or completely negatively charged. The ionic hydrides M plus H minus engage in this kind of reactivity, and many metallic hydrides with transition metals bonded to hydrogen also react effectively in this way, since they've got metal hydrogen bonds that are polarized toward hydrogen, have high electron density around the hydrogen. So the typical idea here is that H minus, the hydride anion, is transferred to an electrophile or acid, usually not through the generation of hydride discretely, unless we're in a solution where the metal hydride dissociates completely, which does happen. So for example, we've got the metal hydride, say it's in solution so that this is actually dissociated. The hydride anion can form a bond to the electrophile, and this curved arrow is showing that pair of electrons in the hydride anion forming a new covalent bond to the electrophile, and the M plus cation here is really just a spectator, right? It's there to hang around, and if we're talking about an ionic or saline hydride, this is something like Li plus, Na plus, K plus, something along those lines. If we swap out this kind of generic looking electrophile or Lewis acid E plus with a Bronsted acid HX, the electron flow changes slightly, but the fundamental idea, particularly from the hydride side, looks exactly the same, right? These electron flows look exactly the same. Hydride donates an electron pair, this time to an acidic proton, and the HX bond breaks toward X. This produces H2, M plus, and although I didn't draw it, should have been drawn in, X minus, the conjugate base of this acid. So this is heterolytic cleavage via hydride transfer. H- in the hydrogen-containing compound is transferred to an electrophile or an acidic proton within a Bronsted acid. Proton transfer is nothing more and nothing less than the Bronsted acid-base reactivity that we've seen previously. So heterolytic cleavage via proton transfer just involves the HX bond breaking toward X. This leaves H without electrons, but typically what happens is a base containing, for example, a lone pair comes along and grabs that H plus so that it's not actually sort of discretely formed, right? So electron flow like this ensures that H plus isn't actually formed, but the net result is the transfer of H plus from HX to the base. So we get the conjugate acid of the base, that's the base H plus, and we get the conjugate base of the acid, X minus, right? And this pair of electrons, this new pair of electrons that shows up at X, came from cleavage of the HX bond in an unequal way, heterolytic cleavage toward the X atom, so that both of those electrons land on X. And this, of course, is typical of Bronsted acids, right? Compounds that contain H linked to relatively electronegative elements like oxygen, for example, are generally going to engage in this kind of heterolytic cleavage by proton transfer, where it makes the most sense in terms of electron distribution in the starting hydrogen-containing compound to break the HX bond toward X, the more electronegative atom in the bond. Now, homolytic cleavage is fundamentally different from heterolytic cleavage in that breakage of the bond occurs such that each atom in the bond gets one of the two electrons in the bond. And this is, by the way, an entirely general term. It does not just apply to hydrogen-containing compounds. Homolytic cleavage can occur in a wide variety of compounds of different elements. But for a hydrogen-containing compound, this is going to lead to a situation in general like you see on the slide, with the bond breaking so that one electron goes toward hydrogen and one electron goes toward whatever hydrogen is linked to. We end up with a hydrogen atom. This is actually a representation of a neutral hydrogen atom with just one electron. And R, this R species with an odd number of electrons, this is known as a radical. This is a little tricky to depict using curved arrows for electron flow since, for example, here and everywhere else we've seen curved arrows, the arrow represents the movement of two electrons. What we do to show homolytic cleavage is use a half-headed arrow to show the movement of one electron at a time. And so essentially here, each half-headed arrow is telling us to take one electron in this two-electron bond and move it, for example, over to H. And this other arrow is telling us to take that other electron in the HR bond and move it over to R. These kinds of fishhook arrows you'll see used to depict electron movements in reactions involving radicals where homolytic cleavage is key. And this reaction type is typical of some metallic and metalloid type of hydrides. For example, tin hydrides are famous for this kind of reactivity. So something like tributyl tin hydride, where these R groups are butyl groups. Don't need to know anything about those. They're really just saturated hydrocarbon groups. If a radical finds itself in the vicinity of a tin hydride, the radical can form a bond to the hydrogen atom. One electron from the tin hydrogen bond goes into that new bond, and one electron from the radical goes into that new bond, and the third kind of odd man out electron just ends up on 10. So we end up with a 10 radical on the product side and a new R prime H bond. And the prime here, by the way, just is used to distinguish between this R group in the radical and the R groups in the tributyl tin hydride. So this kind of reactivity you'll see for hydrogen-containing compounds. We can also think of it, in fact, as hydrogen atom transfer, right? And so in terms of thinking about hydrogen moving around in different ways, we've seen hydride transfer, proton transfer, and the net result here is really hydrogen atom transfer. And this is actually a profoundly Googleable term in 2025. If you Google hydrogen atom transfer, you'll see all kinds of reactions where reagents are used to transfer a hydrogen atom strategically to cause some kind of interesting chemical change, usually at wherever the other radical center ends up. Hydrogen atom transfer is part of the process. Now, oxidation and reduction, we've already studied pretty heavily. We're very familiar with the general definitions of oxidation and reduction. For example, oxidation is the loss of electrons, and we've seen how dihydrogen, H2, can lose 2 electrons to form 2H+. Great example of a classic oxidation reaction. However, there's another way we can think about oxidation in terms of changes in electron density at atoms that are linked to hydrogen versus other elements. So hydrogen, as nonmetals go, is not very electronegative. So if we take, for example, a carbon-hydrogen bond, where carbon is more electronegative than hydrogen, so that the carbon is partially negatively charged in the CH bond, and we replace that H with, say, an oxygen, which is now much more electronegative than carbon, we've actually decreased electron density at this carbon, and that corresponds to an oxidation of the carbon atom. And this is very common. The replacement of bonds to hydrogen with bonds to oxygen or other electronegative elements, nitrogen, the halogens, for example, amounts to oxidation. This also makes sense if you think about the fate of this hydrogen. This hydrogen is often released as H+, and so in a sense it gets oxidized to H+, although its oxidation number remains the same in the course of this replacement with oxygen. On the other side of the coin, we also know very well by now that reduction is the gain of electrons. R picks up an electron to make R-, that's a reduction, and we're familiar with the reverse process, the one we looked at above, that 2 protons can gain 2 electrons to form H2, and this is a reduction process. But we can also flip the idea above on its head about CH and CO bonds and recognize that the replacement of a CO bond in which a carbon is partially positively charged with a CH bond in which that carbon is partially negatively charged, well, we've actually increased electron density at the carbon. The carbon has gained electrons. This is how its charge went from delta plus to delta minus, and that amounts to a reduction. This is a very common mode of reduction that you'll see particularly in organic chemistry courses, and in fact, the reagents used to accomplish these kinds of reductions are often hydride-containing reagents. Reagents like lithium aluminum hydride and sodium borohydride that you'll study in your organic chemistry courses. That hydride is a reducing agent, and it accomplishes its reducing action by replacing, for example, a CO bond, a bond between carbon and an electronegative atom, with a CH bond where the hydrogen is much less electronegative in the product.